We've used some difference equations in defining accumulators and simple systems, running sums. The general form of a difference equation, pulling all the delayed values of the output y to the right side of the equation, plus all the delayed values of the input x, plus the coefficients that multiplies each of those delays, both the delays of the output and delays of the input, is kind of the standard form of a difference equation. And so the final output of all of that, of course, is y of n. And this difference equation draws the block diagram. And so if my input is x of n, I take x of n times b0. And so each of these triangles is a multiplier or amplifier. That's also drawn in some notes just as a solid triangle too, with the coefficient written above it. And so the first thing I see is b0xn. That adds to, well, this z minus 1's a delay, so this is x of n minus 1 at the output of that delay. And so it multiplies b1. So that's the next term in the difference equation, and so forth. And so I have x of n minus 2, and that'll multiply b2, and all those get added together. And so that forms the addition of all the inputs. Same thing at the output. So this is y of n minus 1 after the delay through the z minus 1 times minus a1. And so I get minus a1 y of n minus 1 minus a2 times y of n minus 2. And all that gets added together and added to the input coefficients. And so that forms the sum. And so this block diagram is used to implement a difference equation. Be careful of the sign convention. And so I use negative values here because when you write the difference equation in its usual standard form, you would have y of n plus a1 y of n minus 1 on the left side of the equation equals dot, 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 the positive values of the b. And so when you pull these values to the right side of the equation, the signs flip on the a1, a2, and so forth. And so just be careful. Different textbooks use slightly different conventions. So as an example, we can work with this block diagram and find the difference equation. So we have an input x of n, output y of n. So after the delay block, this must be x of n minus 1 at the output of the delay. That multiplies b1. Again, the solid blocks indicate the multiplier. The solid triangles indicate a multiplier. At the top, b0 multiplies xn. And so these are added together. So I get b0x plus b1x of n minus 1. And then here at the output of this delay, we have y of n minus 1. And so that multiplies minus a1. And that's added to b0 plus b1 x of n minus 1. And so that forms the complete output y after those are all added together. And now I can take the z transform of both sides of this equation. And of course, I get y of z equals minus a1 z to the minus 1 y of z plus b0 x of z and plus b1 z to the minus 1 x of z. Using the delay property, this gives me a z minus 1, and the delayed y gives me also a z minus 1. And so rearranging this, and factoring out y of z and x of z, I can solve for the ratio of the output over the input, y of z over x of z, and that's the transfer function of this block. And so if you rearrange that, you get b0 plus b1 z to the minus 1 divided by 1 plus a1 z to the minus 1. And so this is the transfer function for the block above. So once you have the difference equation, you could also just take the z transform directly. So in essence, we did that when we looked at the block diagram. We found y of n, and then we took the z transform, and when we had y of n minus 1 by the delay property, we had z to the minus 1 y of z. Y of n minus 2 would similarly give you z to the minus 2 y of z by the delay property, delay of 2. And same thing with the delays of x of z's. And so in general, if we have a larger polynomial than the example we had before, the numerator will be the sum of the b's, coefficient b sub alpha times z to the minus alpha. And so those b's are b0, b1, b2. And then on the denominator, we'll have the coefficients a, a1, a2. This sum is from 1 to n. The sum of the b's is from 0 to n, where again, we don't have an a0. We have a0 equals 1, if you wish. Since the y of n is the left side of the equation, it doesn't have a coefficient. If it did have a coefficient, you could divide both sides of the equation by that number to get it in the standard form, because the output, of course, is y of n and has no coefficient a. So one last thing, because I used the minus signs here, if you look at the example we did before, I have a positive sign in the denominator. So all the coefficients have plus values times the values of a. In some textbooks, they will use positive values in a block diagram, in which case you might see a negative sign here in the denominator, 1 minus that summation. So be very careful, depending what books you use, to see which notation is used in the definition of h of z and in the block diagram, whether there's a sign change in the feedback. By the way, these terms A are the feedback terms because the output is being fed back into the circuit. These are the feed forward terms because you're just using delays of the input. Comment on x of z, which you had mentioned a little earlier. If we recall, the frequency discrete time Fourier transform corresponds to x of z on the unit circle, where the angle of that point on the unit circle is the discrete time frequency. And so the point where omega equals 0 corresponds to z equals 1. Of course, that's the DC response of the system. It's very simple to calculate. Just substitute 1. By the way, the DC response of the system is also can be found by substituting z equals 1 in the definition of the z transform. And so the DC response of the system is just the sum of the values of the x of n's. And so let's say, for example, if I have x of z is z over z minus 0.1, the DC response of that system, just substitute z equals 1, is 1 over 0.9. Similarly, at z equals minus 1, that corresponds to the frequency response at omega equals pi. And so if you recall, omega equals pi radians per sample. That's the fastest frequency in a discrete time system, would correspond to a sequence of 1 minus 1, 1 minus 1. So here's another example using fixed values for the weights in the system. And so x of n is multiplied by 6. X of n minus 1 at the output of this delay is multiplied by 5. The feedback is multiplied by a half. And so I get y of n minus 1 over 2. And again, all those are added together to form y of n. And so from this, we can find y of z using z transform property. So I get z to the minus 1 times y of z for y of n. I get x of z for the z transform of x of n, and z to the minus 1 x of z for the z transform using delay property of x of n minus 1. Then I can rearrange this, solve for the ratio of y over x. So output over input is the transfer function of the system. And so in terms of z minus 1 would be 6 plus 5z minus 1 over 1 minus z minus 1 over 2. But I can multiply top and bottom by z and get it into 6z plus 5 divided by z minus a half. And so we can see the pole for this system is that z equals 1/2. So this is a causal system. Since this block diagram, of course, has to be causal. And so the magnitude of z must be greater than 1/2 because the pole is at the boundary. There can be no poles in the region of convergence. So that sets the ROC for the system. So we can calculate the impulse response from the diagram of the system. And so I'll show how to do that. So if I put an input in, it's an impulse. So I just put a 1 into the system. It's linear time invariant, so it can't have any non-zero initial conditions. So the output of the two registers, the two delay registers, we'll assume is 0. And so then the first output must be 6. The clock then stores the values in a register. So the incoming 1 is stored in this register. So I have a 1 at the output of the register. The next input to the system is a 0 because the impulse is only 1 for the first time step at the input. So in this condition, I have a 0 at the input, a 1 at the output of the register. And then similarly, the 6 that was at the output now is stored in the register at the next clock cycle. So I have a 6 at the output of the register. And that's multiplied by a half. And so I have 1 times 5 plus 6 times a half. So my next output is going to be 8. So these are n equals 0, n equal 1. At the next clock cycle, the 0 that was coming in becomes stored in the register. So the register output becomes 0. The 8 that was at the output now is stored in the register, and I have an 8 at the output of the register. And so the front part of the circuit now adds to 0, and the only thing I have left is the 8 divided by 2, so my next output is going to be a 4. And notice that the next clock cycle, the same thing happens. Nothing will happen at the input because zeros just keep coming in. And so at each clock cycle, the value gets stored and reduced by a factor of a half. So the next output is 2, and so on. So I get 8, 4, 2, 1, etc. And so this is the impulse response of the system working from the block diagram. By the way, the system is stable because Uh, the sum of these values is going to be bounded. It looks like a sequence um, that would be, at least from this point onward, this would look like a sequence of 8 times 1/2 to the n. And so the 1/2 to the n sequence has an infinite sum of 2. And so you can work out that that infinite sum of the sequence plus the leading value of 6 is going to be bounded. By the way, it's also stable because the poles are inside the unit circle. It has only one pole, that's at z equals 1/2. And so if I plot that on the unit circle is going to be out here. The z equals 1/2 is going to be inside, and the region of convergence will be from 1/2 outward, which will obviously include the unit circle. We can also do an example where we find a block diagram based on a z transform. And so if we have y of z over x of z is a sequence of a to the n u of n, it's 1 over 1 minus a z minus 1 for the lookup table, which would look like z over z minus a. And so we can draw this straight from the z transform. And so since h of z is y over x, that would mean y of z times 1 minus az to the minus 1 equals x of z, or y of z equals x of z plus az to the minus 1 y. Well, we just draw an input and an output x and y. Here I say I need z to the minus 1, so I add a z to the minus 1 block on the y side. I multiply by a, and so I add that to x of z. And so the z transform can be used to draw the block diagram for implementing the system. And so once I have the block diagram in z, I can do the same thing and take the inverse z transform. Of course, the input is x of n. The output is y of n, taking the inverse z transform. This is a delay block, and so this output will be y of n minus 1 and multiplied by a. And so I can also write the difference equation once I've taken the z transform, draw the block diagram, and then take the inverse transform. If I look at this block diagram, I can calculate the impulse response. So if I put a 1 into the system, the first output is going to be a 1. That 1 gets stored in the register, then it multiplies a, and so my next output is going to be a. That a gets stored in the register, the next output is a squared, and so see that indeed you can calculate h of n now from the block diagram of the system. By the way, from this simple example, if a is 1/2, then the sequence would be 1, 1/2, 1/4, well-behaved sequence. If a was 2, then the sequence would be 1, 2, 4. It would be a diverging sequence. And so this feedback, of course, determines that behavior and is the primary factor in determining the stability, bibostability of the system. So now we can take a look at the important example of an accumulator or running sum. And so the formula for an accumulator is the output is the sum of the inputs x from minus infinity up to the current time point n, because the output at time point n is the sum up to that same time point. One way to view this is a machine that goes along and it adds all the values up to the nth point, and then the output at that point, the output y, is the sum of all these values up to the current time point. And so these would be the x's. The next output would be the sum all the way up to the next point, and that summation would produce the next output at the next time point. And so an interesting example is when the input is an impulse. So we look at the impulse response of this. And so if my input is a impulse, what is the output? And so if this is x and this is y, the accumulator, if I add all the values up to here, well, they're all 0, 0, 0, all the way up to the point where I hit n equals 0. And at n equals 0, I add the value 1 of the impulse, and so that sum becomes 1. If I continue adding to the next time point, I notice that I don't add any more 1s. I always have a sum equal to 1. And so for every time point after that, the output is 1. And so the impulse response to the system is u of n. So how does this change if the input, instead of being an impulse, is a step? And so in this case, we take a look at the output. Now the input is a unit step, starting at 0. And then we take the sum all the way up to this point. And so the sums ahead of 0 are all zeros up until the 0th point, and I get a sum of 1. But the next sum is 2, because I have 2 1s. The next sum is 3, and so I get a diverging ramp when the input is a step. Is the system linear? Yes, it is. If I double the x of n, I can see here that the output would double. Is it time invariant? Well, if I shifted this impulse, then the response to the unit step would have shifted accordingly too. You can prove those by plugging in the formulas and the definitions of linear and time invariant and prove that more rigorously. So this is indeed the impulse response of the system is u of n, since we calculated that by argument. We've showed that the system is linear and time invariant. Is this system bibostable? And the answer to that, we could see several ways. Most straightforward in this case with what we have is, remember, the sum of the magnitude of h of n impulse response must be bounded. And of course it isn't, because the unit step, the sum of the unit step would be infinite. And so the answer to this is no. Is the block diagram correct? Well, let's see if we put an impulse into the system, what comes out. So we put a 1 into the system. The register, of course, if it's linear time invariant, has 0 initially, and the first output of this system will be a 1. A 1 gets stored in a register, and the next input of x for the impulse, of course, is a 0. The 1 gets added to 0, and the next output is a 1, and that repeats itself. And so the 1s keep getting stored in the register and keep getting 1s at the output. And so indeed, this system has an impulse response that's u of n. And so this is an implementation of the accumulator or running sum. By the way, this corresponds to a continuous time system. And so, of course, the impulse response of the accumulator is a unit step. If we remember, if we have an integrator and the input to the integrator is an impulse, The output of the integrator is a unit step in continuous time. And so the accumulator in discrete time behaves as a very similar to an integrator behaves in continuous time. So it's analogous to the integrator of continuous time, and the accumulator serves a similar important role in systems that an integrator does in continuous time systems. Another important system is the backward difference. And so backward difference is defined by this difference equation. The output is x of n minus x of n minus 1. I think it's easiest to see this as a word problem. The output is today's stock price minus yesterday's stock price. So it's a difference in values, and measures change. I can take the z transform of that equation directly. So I get z to the minus 1 x of z for the delayed portion. And so y of z is 1 minus z to the minus 1 times x of z. So the transfer function is the output over the input. So that's h of z. It's just 1 minus z to the minus 1. I can find the frequency response of this system. Remember, h of omega is h of z at z equals e to the j omega. So it's just 1 minus e to the minus j omega. If I split the exponents, then I have multiply by e to the minus j omega over 2. I can use Euler's identity. Taking the magnitude, the j goes away, and I just get 2 sine of omega over 2. By the way, the magnitude of e to the j theta is 1. It's on the unit circle, so e to the j omega 2, similar. And so the frequency response to this backward difference at omega equals 0 is 0. And so here we have a plot at omega equals 0. It has a sinusoidal shape. Of course, it's the magnitude of the sine, so it's positive in both directions. And at the highest discrete time frequency, omega equals at omega equals pi, I have sine of pi over 2, which of course is 1. And then that's times 2, so the frequency response at the highest frequency is 2. So we can see this is a high pass function, and the response of this function is 0 at DC. And so this again is a linear time invariant system, and it looks a lot like the derivative, if you recall. If you have the d over dt, if you take the Fourier transform of the derivative transfer function, it gives you 1 over j omega, or 1 over s in Laplace. Excuse me, that should be 1 over j capital omega, since that's a continuous time response. And so the plot of the magnitude of 1 over j omega would be a straight line. And we see that this Fourier, discrete time Fourier transform of the backward difference has kind of the same basic properties of a derivative, in that it has 0 response to DC. Of course, if I put a DC voltage into a differentiator, the output is 0 because the slope is 0 on a DC line. And so this backwards difference, which measures change, acts a lot like derivative. To show this even further, let's take the convolution of the backward difference with a ramp, a finite length ramp. And so the impulse response of the backward difference, there are several ways to do it. One simple way is to say that the h of n is y of n when the input x of n is a delta function. And so if I just replace these these x's by delta function, the impulse response is delta of n minus delta of n minus 1. And of course, in my shorthand notation, that would be a 1 at 0 and a minus 1 at n equals 1. And so this would be the impulse response of the backward difference. And to find the output, it would just be the convolution with some input x of n, which we choose here to be a finite length ramp. And so to do this convolution, I'll just do this using my bracket notation. So the h of n's will serve as my weights, and so I just have 1, 2, 3, 4 for the unshifted convolution first step. For the second step, I have a weight of minus 1 that would multiply this shifted by 1. And so I have minus 1, minus 2, minus 3, and I got to take this one further, minus 4, so let's put a 0 here. And then I add all those together as the total response. And so if I add those together, I would have a 1, 1, 1, 1, minus 4. And so if I draw that down here, 1, 1, 1, minus 4. Does this look like the derivative? And indeed it does. What is the slope of this ramp? Well, the slope or the change between 0.1 and 0.2, the slope is 1, and so I have that here. The slope between beginning at the left, going from 0 to 1, I have a 1. Going from n equals minus 1 to 0, I have a difference of 1. From going from 0 to 1, I have a difference of 1 again. And from 1 to 2, I have a difference of 1 again. And from 2 to 3, I have a difference of 1 again. And then finally, this last step, I go from 4 down to 0. And so this is my value of minus 4 for this last time point. And so indeed, the backward difference behaves as we expected. It's essentially a measure of the derivative or the slope of the ramp. This last step, of course, is just an indication that the ramp slope went quite negative. It went from a value of 4 to 0 in one step. Finally, what's the block diagram of this system? So we can write it just straight from the Z transform. So this block diagram of this system would be x of n, or x, easier to work in Z, so x of z, coming at the input, z minus 1, and then feed forward to a summing junction, and the output is y of z. And now my weight, since I subtract the delayed version, would be minus 1 in the delayed input side. And so I can draw the block diagram straight from the Z transform. By the way, all h of omega DTFTs are periodic. And so, of course, this would repeat again at 2 pi and pass through 0 again. And so this will be a periodic response. This is definitely not a low pass filter, so it passes high frequency. And the DC response is 0. As we've seen in some of these examples, you can directly solve for h of z from the difference equation. So if we have a 4-point sum as our system, so the output is the sum of today's, yesterday's, the day before, and a day before that. We could rearrange this a couple different ways. If I just look at what y of n minus 1 is, then notice that I guess x of n minus 1, 2, 3, and 4. If I take the difference of these first two results, y of n minus y of n minus 1, notice that the x of n's will cancel, the x of n minus 2 is the x of n minus 3, and so that must just equal x of n minus x of n minus 4. So now I have a new difference equation that solves the same problem. And so these two are equivalent. So this first equation up top, difference equation up top, is equivalent now to this equation below. This is a key thing about difference equations. They are not unique. And so the choice of difference equation is the art of engineering. And so some may require less hardware, some may be more efficient, some may require more computation. And so the non-uniqueness is a good and bad aspect. The bad aspect is there's not a unique solution. The good aspect is it allows you multiple solutions, and so it's left to you to choose the solution that best suits the needs of the problem that you're working on. So if we go with the second form, so we just rearrange this, we can take the z transform of both sides of the equation and solve by rearranging the equation. We can solve for y of z in terms of the x of z. And so the output must equal the transfer function times the input. And so this portion is the transfer function h of z. This h of z has a transfer function 1 minus z to the minus 4 over 1 minus z to the minus 1. We've seen this before. This is the example when we took the z transform of a sequence with 4 ones between 0 and n equals 3. And so it has a pole zero cancellation. So it has a triple pole at z equals 0, and it has 3 zeros at z equals j plus j and z equals minus 1. The DC response is a little difficult to see in this form because I have 1 minus z equals 1, so 1 minus 1 at the denominator if I evaluate this DC response. However, if we come up with the original z transform up here, we can note that if we take the z transform of the top equation, y of z equals x of z times 1 plus z to the minus 1 plus z to the minus 2 plus z to the minus 3. And so in this form, the transfer function, we replace the z's plus 1. We can see that the response h of z is going to be 4 at z equals 1. So the DC response is easiest to see if we take the z transform of the equation we started with. And so here we can say the DC response is 4 for this system. Another way, if you recall, is the DC response is the sum of the impulse response of the system. And again, h of n for the impulse response equals y of n when x of n is a delta function. So if I replace all these x's by deltas, h of n equals delta of n plus delta of n minus 1 plus delta of n minus 2 plus delta of n minus 3. And so that's what leads to these four delta functions. Their sequences. The sequence is 1, 1, 1, 1 in my bracket notation. And so we did an example like this when we took the discrete time Fourier transform examples. So next, the inverse transform. The first method for inverse transform